In this section, we will talk about acids and bases. A lot of this is a review from Unit 2, and how to actually calculate the quantitative pH value. Remember that an acid, according to Arrhenius, is a substance that produces hydronium ions when dissolved in water. Let's say, for example, we add hydrogen chloride to water. We know that that will split apart into the hydrogen and the chloride ion. Those hydrogen ions will attach to the water molecule to form the hydronium ion. Arrhenius also defined a base as a substance that produces hydroxide ions in water. We've seen that NaOH, when dissolved in water, this is an ionic compound, will split apart into the sodium and the hydroxide ion. We've also looked at how NH3, when dissolved in water, will also produce hydroxide ions. Those hydroxide ions floating around signify a base. There is another definition of an acid and a base. According to Bronsted-Lowry, an acid is a hydrogen or a proton donor, and the substance that remains after the hydrogen has been donated is called the conjugate base. Let's take a look at the example below. If we take a look at the reactants and products, we'll notice that there are similar species on each side. We want to connect those. So I'm going to take the ammonia and connect it to the ammonium ion, and I'm also going to connect the water with the hydroxide ion. These are pairs that represent acids and bases, and conjugate acids and conjugate bases. You can see here that water is giving up its hydrogen to ammonia, and we know that because water on the other side is hydroxide. So in this case, water is going to act as the acid. And then the particle that remains after the hydrogen has been donated is called the conjugate base. According to Bronsted and Lowry, a base is a hydrogen or a proton acceptor, and the substance that forms after the hydrogen has been accepted is called the conjugate acid. So looking at the same example, you can see here, as we draw the connections between the species that look identical, you can now see that the NH3 has become NH4+. It has accepted a hydrogen, thus it is a base, and the particle that remains after the hydrogen has been accepted is the conjugate acid. Don't forget, in the other example, water was acting as an acid, and hydroxide was acting as the conjugate base. Let's try a few examples. One of the things you want to remember are acids and bases will always be on the reactant side, which is the left side of the equation, and conjugate acids and bases will always be on the right side, which is the product side. What we're going to do is label the acids and base on the left of each of the examples below, and the conjugate acid and the conjugate base on the right. We'll start off by making the connections between the substances that look the same on the reactant and the product side. You'll notice that the HCl becomes Cl-. That means that it has donated a hydrogen, and so it is considered the acid. The chloride ion will then be considered the conjugate base. The other species on the left must be the base, and if we double check, you will see that the H2O has become H3O+. Thus it has accepted a hydrogen ion, and the particle that remains is the conjugate acid. In the second example, we'll do the same thing. We're going to connect the species that look similar to one another, and when we compare the HCO3, which is a bicarbonate ion, with carbonic acid, you will see that it has accepted a hydrogen ion on the product side, which means the bicarbonate ion is acting as a base, and carbonic acid is the conjugate acid, leaving us behind water, which must be the acid. And if we look closely, you will see that it's become the hydroxide ion, it has lost a hydrogen, so this is going to be your conjugate base. This table should look familiar to you. It is a list of all the characteristics of acids and bases. Remind yourselves that acids produce hydronium ions in water. They taste sour. They react with active metals to form hydrogen gas. They turn blue litmus paper red. they turn clear in phenolphthalein, which is an indicator, and they react with bases to form salt and water, which is called a neutralization reaction. Bases, on the other hand, produce hydroxide ions in water, taste bitter, feel slippery, turn red litmus paper blue, they turn pink in the presence of phenolphthalein, they react with acids to form salt and water, which is a neutralization reaction, and you need to remember both acids and bases are considered electrolytes. They do conduct electricity. When they get dissolved in water, they will release. A strong acid will have more ion pairs than molecules. You can see in this example, we've got 1, 2, and 3 pairs of ions versus 1 intact acid molecule. In a weak acid, you're going to have more molecules than you will have dissolved ion pairs. You can see here there's only 1 dissolved ion pair, and we have 3 intact acid molecules. Strong acids and bases are strong electrolytes. Lots of ions floating around, lots of electrical conductivity. Weak acids and bases are weak electrolytes. Very little ions floating around, very little electrical conductivity. Earlier in the year, we learned about the pH scale and its ability to measure the acidity of a sample. We learned that it ran from 0 to 14, and that acids had a pH value that ranged somewhere between 0 and 6.99, and that bases had a pH value that ranged somewhere between 7.01 and 14. If the pH was exactly 7.0, it was considered neutral. We also learned that the strength of the acid and the base will increase as you get closer towards the ends of the number line. For example, a pH of 1 will be stronger than a pH of 6 when it comes to acids, but a pH of 8 will be a weaker base than a pH of 13. In the next couple of slides, we're going to learn how to calculate the pH value. pH stands for power of the hydrogen, and pH scales are logarithmic scales where you're going to use the base of 10. Below, you will see 2 very important equations. pH is equal to the negative log of the hydronium ion concentration. The brackets represent molarity. And then hydronium ion concentration is equal to the inverse log of pH, which would be represented as 10 raised to the negative pH value. Look at the graph below. You will see that there is an inverse relationship between hydronium ion concentration and pH. As the pH value increases, you will see that the hydronium ion concentration decreases. So what does a log scale really mean? Well, every change of 1 in pH shows a change of 10 times, a factor of 10 in concentration of hydronium ions. If we take a look at the chart below, remember that a pH of 1 will have more hydrogen ions than a pH of 4. If we take a look at the difference between a pH of 1 and a pH of 2, that is a change of 1, so we would say that a pH of 1 is 10 times more acidic. If we take a look at the difference between the pH of 3 and 1, that would be a difference of 2. 10 to the second is 100 times. So a pH of 1 is 100 times more acidic than pH of 3. And if we take a look at the last example, where we compare 4 to 1, that is a difference of 3, and 10 to the third is 1,000. So a pH of 1 is 1,000 times more acidic, has 1,000 times more hydrogen ions than a pH of 4. Let's try this example out. The pH of a solution changes from 5 to 3. Did it increase or decrease in hydrogen ion concentration, and by what factor did it change? Well, we know as we decrease in pH, we're becoming more acidic. And when we become more acidic, that's going to increase the number of hydrogen ions. Well, what factor did it change by? Well, we know 5 minus 3 is a difference of 2, and we know that every unit change of 1 is 10 times, so 10 to the second would be 100 times. Alright, so let's take a look at some examples that you will need to be able to do. The first is finding the pH when given the hydronium ion concentration. Remember the equation from earlier, pH is equal to the negative log of the hydrogen ion or the hydronium ion concentration. In this example, they're giving you that value, so you're just going to plug this in to the equation, and then you're going to use your calculator to solve. So take out your calculator, push the negative sign, and then find the button on your calculator that says log. Press that, and then enter 1.0 e negative 8. Press enter, and you should get a value of 8.00. You might be wondering why I put a double zero on the end. Well, significant figures in logs are a little different than normal numbers. Because the hydrogen ion concentration has 2 sig figs, we always make sure that the pH value has 2 sig figs to the right of a decimal point, in this case 0, 0. In this next example, we're going to do the reverse of what we just did. Now I'm giving you the pH, and you need to find the hydronium ion concentration. So going back a couple of slides ago, you will remember that you saw that the hydronium ion concentration can be solved by taking 10 and raising it to the negative pH value. In this case, the pH is 5, so we're going to take 10 to the negative fifth. You'll put that into your calculator, and your calculator will give you 1 times 10 to the negative fifth. Of course, this is molarity because we're working in concentration. Your calculator might also give you 0.00001 m. Don't forget that those two numbers are the same. This is in scientific notation, this is in ordinary notation. Before we do any other calculation, we need to talk about what autoionization of water is. Naturally, water molecules will collide with each other, and probably once out of every couple million collisions, you will get two water molecules to split into the hydronium and the hydroxide ion. This is called autoionization. That is why pure water is considered neutral. There is the same amount of hydronium ions as there are hydroxide ions floating around. This occurs at 25 degrees Celsius. It makes this statement true, that hydronium ions and hydroxide ions, when multiplied together, will always have a product of 1 times 10 to the negative 14th molarity squared. Now this is called Kw. It is the equilibrium constant for water, and you just need to know that it is a constant and that it is provided to you on your reference sheet. So let's look at hydrogen ion concentration values. For an acid, which would have a pH of less than 7, the hydrogen ion concentration must be greater than the hydroxide ion concentration. The hydrogen ion concentration will also be greater than 1 times 10 to the negative 7th molarity. An example of this would be when a hydrogen ion concentration is equivalent to 1 times 10 to the negative 3rd in molarity. For a base, the pH will be greater than 7, and the hydrogen ion concentration will be less than the hydroxide ion concentration. The hydrogen ion concentration will be less than 1 times 10 to the negative 7th. An example of this would be something like 1 times 10 to the negative 11th in molarity. And if your solution is neutral, the hydrogen and the hydroxide ion concentration will equal to each other, and a pH of 7 will exist. This slide shows you the equations that you will use to calculate pOH. You'll notice that these equations are very similar to the ones that we use to calculate pH. The only difference is the introduction of the hydroxide ion. At the bottom, there's a very important equation that we will use later on, and this relates pH values to pOH values. All of the equations that I've showed you thus far are on your reference sheet. So let's take a look at this example. It says find the pOH if the concentration of the hydroxide ion is 1 times 10 to the negative 5th. So we know that pOH is equal to the negative log of the hydroxide ion concentration. So since they've given me the hydroxide ion concentration, I'm going to substitute that number in, and I'm going to use my calculator like before. I'm going to put the negative button in, I'm going to press the log button, I'm going to type in 1e negative 5, and I will end up getting 5.00 as my answer. Remember again that however many sig figs you have in your concentration, that's how many digits you need to express your answer to the right of the decimal point. This is only a technique that is used when working with logarithms. In this next example, they're asking you to find the POH. Remember the new equation I introduced to you a few minutes ago? POH plus pH equals 14. Since they're giving me a pH of 4, all I need to do is figure out what the POH is by subtracting 4 on both sides. That will then give me a POH equal to 10. In this next example, I'm given the hydrogen ion concentration, and I need to find the hydroxide ion concentration. There is a couple of ways to do this. The first way would be to go back to that original equation where we said 1.0 times 10 to the negative 14th molarity squared was equal to the hydrogen concentration times the hydroxide ion concentration. In this case right here, we would take the value of 1 times 10 to the negative 9th, plug it into the equation, and solve for the hydroxide ion concentration. In order to do that, I would divide both sides by 1 times 10 to the 9th. And the great thing about these simple numbers that we're working with right now is that we really don't need a calculator. The hydroxide ion concentration, 1 divided by 1 is 1. When we're dividing two numbers in scientific notation, we subtract the exponents from each other. So negative 14 minus negative 9 would give me 1.0 times 10 to the negative 5th as my answer. There's a second way to do this problem, and even though it looks like a lot more work, people tend to go this route once they get comfortable with these equations. Given a hydrogen ion concentration of 1 times 10 to the negative 9, we can then pop it into the equation. pH is equal to negative log of the hydrogen ion concentration, and that will give us a pH of 9. We can then use this next equation, POH plus pH equals 14, to get a POH of 5, with the final equation of popping in the 5 as the negative POH and coming up with the answer of 1 times 10 to the negative 5th. It's your decision on which way you want to do the problem. Just make sure you pick the way that gets you the right answer. In this last example, it says what is the pH if the concentration of the hydroxide ion is 1 times 10 to the negative 7th. We need to be very careful and understand that pH is the power of the hydrogen, and you've been given hydroxide ion concentration. If we use the equation POH is equal to the negative log of the hydroxide ion concentration, we can substitute in the numbers. You will find out that the answer comes out to 7.00. Using the equation pH plus POH equals 14 will then allow you to realize that if my POH is 7, my pH will also have to be 7 in order for this equation to work out. Okay. If you had used pH is equal to the negative log of the OH, okay, you would find that you are not going to get the right answer because these do not match. So be very careful about the equation that you pick. When you're solving for pH, you must use the equation that shows the hydrogen ion. If you're solving for POH, you must use the equation that solves for the hydroxide ion. We'll do a lot more practice in class, but this will get you started. See you then.